Hello, everyone. We are Team NASA Treadmill. We were tasked with developing an alternative exercise device to the treadmill currently being used on the International Space Station, which helps astronauts stay healthy on long-duration space missions.
Our team is made up of 4 students. We are Caroline O'Connell, Justin Teague, Zachary Arsment, and Sammy Diab. Our faculty advisor at the University of Texas is Dr. Eric Taliff. He is a professor in material science, and he focuses on the mechanical behavior of materials. In addition, our NASA mentor is Flight Chief Philip Callan.
We're looking at ways of preventing the negative long-term health effects of spaceflight. In studying astronauts that have been up on the ISS for 200 days or beyond, it's been observed that astronauts can lose bone mass. They can reduce this by running on a treadmill. The impact forces of running create shocks in the bone, forces the bone to rebuild and repair itself. And this stops calcium from being leached in the bloodstream and then exiting the body. Also, running on the treadmill on the ISS helps astronauts maintain their balance. It helps them maintain their sensory motor systems and maintain cardiovascular health. We've been tasked with coming up with an innovative design that's both reliable, safe, and provides an enjoyable form of exercise.
While current space treadmill designs are appropriate for large vehicles like the International Space Station, they're not suitable for future space exploration vehicles. New size, mass, and power consumption constraints have forced NASA engineers to rethink ways of keeping their astronauts healthy while out on missions. For this project, our team will aim to design an innovative non-treadmill concept that will provide a treadmill's physiological benefits in a microgravity environment while using fewer resources than current spaceflight treadmills. Our primary requirement for this project is to design a non-treadmill concept that delivers the same physiological benefits that an ordinary treadmill would. These necessary physiological benefits include reducing the degradation of bone structural strength, sensory motor control systems, and cardiovascular fitness. Metric constraints for this design include a volume of less than 50 cubic feet, power consumption of less than 500 watts, a weight of less than 100 pounds, and a project cost of less than or equal to $500,000.
After identifying the requirements of our design project, we set about brainstorming. In order to do this, we used a concept generation tactic called 635, which gave us 4 different device design ideas, including the Astro Ninja, which is essentially a standing machine that allows for the astronaut to repeatedly break a board by kicking it. We came up with the light dance idea, which is very similar to the commonly known game of Dance Dance Revolution. We came up with the rowing and biking machine, which is a device that combines both a rowing machine and a seated step machine. And we came up with the Not a Treadmill, which works very similarly, in which the astronaut runs with a moving floor, but instead of the regular mat that a treadmill uses, this is 2 different platforms that are moving with the feet of the astronaut in order to take up less space.
In order to determine which concept we should go with, we tried some quantitative analysis based on the different modes of exercise. Running has an advantage in that it provides a pretty high impact force of about 1.5 times your body weight at a really high cadence of about 180 steps per minute as well. The other mode of exercise that most closely matched to this is dancing, and that it provides even slightly higher body weight force, and then also a similar cadence to running.
We created a pew chart with all the main functionalities that we wanted our device to achieve, and we listed the weight of how those devices met those required needs. And by creating a sum weight, we determined that the light dance best met all the functionalities compared to the other 3 devices. Next, we created a house of quality to compare our design, the light dance, to the 3 current devices already used in the ISS. And this consists of the Colbert treadmill, the Ceves, which is a biking machine, and the ARAD, which is a resistive weight device. And we determined that our device met all the required needs better than the 3 current devices used.
We need a way for our astronauts to interface with the machine, a way for our astronauts to provide useful information to the machine. Firstly, we need to position the astronaut on the dance platform. You can accomplish this by using infrared telemetry and triangulation. And we need a way to measure the impact forces of the astronaut dancing on the platform to make sure that they're high enough. We can accomplish this with a set of 4 S-shaped load cells positioned on the 4 corners of the dance platform.
When it comes to machine to astronaut information, we are envisioning an experience that not only improves the astronaut's experience, but also improves the astronaut's overall performance. Our 2 ideas when we were thinking about this were virtual reality and a screen placed in front of the astronaut. We are envisioning an idea such as something similar to the commonly known game of Temple Run, in which the astronauts are viewing obstacles that they need to move around or jump over. When considering virtual reality versus the screen idea, we took into consideration things such as cost and overall performance. We identified the virtual reality experience as offering a much better performance than the screen, and due to the fact that the NASA budget will allow for this superior alternative, we have decided to ultimately go with the virtual reality idea.
We took another look at the harness currently being used to hold astronauts down when running on the treadmill on the International Space Station. Common complaint was that in order to get a high percentage of gravity simulation, astronauts would get some pressure points on their shoulders and on their hips. So we looked at changing this type of harness over to a body wetsuit, where the webbing would distribute forces around the hips, around the shoulders, and then also now to the head, as your head represents about 5 to 10% of your body mass.
Our device is ultimately a platform on which the user would stand. Underneath this platform is a 3D printer-like mechanical system that moves a magnet in 2 dimensions so that the magnet is always located beneath the user's center of mass. A sister magnet located on top of the platform mimics the movements of the first magnet. The user would connect the second magnet to a handle located between the astronaut's legs on the wetsuit via a bungee cord. And in this way, we could enable the astronaut or the user to perform all the movements and actions that are required.
To determine if our plate was strong enough to hold the user jumping around on this plate, we simulated 365 pounds hitting the very center of the plate, which is a worst case scenario of an adult male jumping right where the magnet is. So we found that there's a maximum displacement of 0.918 millimeters, which is key because we want to make sure that there's very little displacement. So the 2 magnets, the top and the bottom, are close enough to one another, and the plate doesn't displace and interrupt that interference. We also determined that the maximum stress is 18,000 psi, which is less than the yield strength of 66,000 psi. So we know that the plate will not fail.
Overall, we set out to decrease the volume, weight, and power consumption of this exercise device when compared to the current treadmill that is being used by NASA. We have our desired values here, and these were the maximum values we were trying to reach, but ultimately we are very satisfied with the fact that our achieved values are much lower than these desired values, as you can see in this table, in which the percentages are much lower and therefore very successful when it comes to all 3, the volume, weight, and power consumption of our dance device.
Thank you everyone for tuning into our presentation. We'll be hosting a question and answer session from 5 o'clock to 7 o'clock this evening, and we look forward to seeing you there. Thank you for your time and have a wonderful day.